And all right, so today we continue with our lectures on computer arithmetic. I don't know if you have any questions up to now regarding past lecture, any confusion, anything you would like to highlight. If no, if you are silent, I assume that everything is fine. Just feel free to interrupt at any point, okay? So, it doesn't work very nicely. Just a second. It's a bit slower. Why? Let's try one more time. It's a bit slow when I do it like that, but it is fine. Okay, what we did, basically, I try to highlight like how we convert numbers from one number system or base from one base to another, right? Now I assume that we are familiar with converting numbers, decimal numbers to binary or binary numbers to decimal. We had some examples. Things are a bit slow, why I didn't understand, but anyways, let's go ahead. And I have demonstrated two algorithms to convert a number in decimal to binary, right? We can perform continuous subtraction and also continuous division to have the conversion. You are familiar with those conversions, I assume, right? I highlighted, for example, if we have n-digit numbers, for example, decimal number, how many numbers can we represent using 10 digits? What is the range of numbers? I assume that we don't have any problems with this. I have already highlighted, for example, for an n-digit decimal number, we can represent n to the power of 10 to the power of n values and different numbers. And the range of numbers that we can represent starts from 0 to 10 to the power of n minus 1, right? You can also think as simple example, for example, 3-digit number, and you can basically generalize the range and the range of values for an n-digit number. So we also highlighted base 16. We told that in base 16, we have, let's say, digits from 0 to 15. That's why after 9, we represent these numbers using letters, right? This is something that we are familiar with. So if we have base 16, it means that each digit is represented by 4-digit binary number, right? For example, F represents 1, 1, 1, 1, 15. D represents 1, 0, 1, 1, 0, 1. What is the 13th, right? And we also highlighted conversion from hexadecimal to binary, binary to hexadecimal. We have a kind of shortcut. We don't need to convert a number in hexadecimal system into decimal, then convert it back to binary. We can group, or we can just represent each digit, right, using a binary number, its corresponding binary number, and then we just group and we obtain already the conversion from hex to binary or binary to hex. We highlighted bytes, nibbles, powers of 2. I don't know why things are a bit slow today. I am just pressing the button, but it doesn't react immediately. In the last part of the lecture, we dealt with addition, adding binary numbers. We thought that if we have a fewer number of digits, if the sum is larger than the available number of digits that we have, there is overflow. We need to take into account that. For example, I highlighted that if you add, for example, what is this number in decimal? What is that? What's that? What is this in decimal? 11. So I have a problem with my computer, unfortunately, but let's see. And this is, what is that? What? 6, 11 plus 6 is 17. 17 cannot be represented by a 4-digit binary number, 17. Can it fit? The largest number that we can represent using 4-digit is 15, right? That's why if we have 17 as a result of sum, it looks like it will not fit in 4 digits. So that's why we have an OR. The result, the sum will not fit in available number of digits. And I have shown subtraction and we have, yes, I think approximately here we finalized our lecture. So let's consider multiplication. I mean, how multiplication can be performed. This is also something we are familiar with. I mean, how we multiply two binary numbers. Basically, we need to know that 1 multiplied by 1 makes what? 1. And 1 multiplied by 0 makes 0, right? This is what we do here, actually. Like 1 multiplied by 1, we have 1, 1 multiplied 1, we have 1, 1 multiplied by 0, we have 0, 1 multiplied by 1, we have 1. And then we just shift one column and then we multiply things. Multiplication by 0 is equivalent to, just filling things with 0, 0, 0, 0, 0, and 1 multiplied by 1. Basically, multiplication with 1 gives you the number that you are multiplying. Multiplication with 0 gives you just zeros, right? If you write things like that and then perform binary addition, but now, as you see, you perform binary addition using not two bits, but 3 bits. What you have the result, the sum, which is the product, basically. So 1 directly here, 1 plus 0, 1, 0, 0, 1, 1, 1, 0, 1, next 2. You have 0 here and a carry plus 0 plus 0, it makes 1, and another one here. And this is like basically the product, okay? Nothing is different than multiplication in decimal number system, but now we have different digits, 0 and 1, which makes us, consider different combinations. Clear? You can also cross-check. I mean, if you are not sure, convert, base 2 numbers, digital numbers, binary numbers into base 10, make multiplication in base 10, and you can convert things back to binary. This is also another way to do things. You can be more sure about what is happening, basically. And we have some shortcuts. For example, if you multiply by 10 a number in decimal system, right? For example, 125 multiplied by 10 corresponds to just shifting the number 1 column to the left, right? I mean, we just shift that number to the left and we add a 0, basically. So if you multiply by 100, it means that you shift the number 2 columns to the left and you add 2 zeros. So this is the same also for base 2 or binary numbers. So multiplication by 10 is equivalent to shifting by 1 column to the left. Multiplication by 100 is shifting the number 2 columns to the left. Multiplication by 2, a binary number, corresponds to, again, shifting the number to the left by 1 column, right? So 1, 0, 1, 0. If you multiply it by 2, right? So what does it mean? Like 1010, what is that number in decimal? What is that? 1010, 10, right? So if you shift that number to the left and add 10, 10100, what does it correspond to? Now, if you convert that number back in binary, what is that? What is that number? Can you tell me? 16 plus 4, it is 20, right? 20. So basically, I shifted 1010 to left, and I put a 0. Then that shifting operation is equivalent to multiplication by 2, right? We see it by example. And also, like, if you shift a number one column to the right, for example, like rather than, for example, if I have this number, I shift it by to the right, and I obtain this number. So let's see what is the effect. So 1011, what is that in binary? 11. This is 11. And what is that number when I shift it to the right? That number, 1 bit. What is that? 5, right? 5. So basically, like it has an effect of like dividing the number by 2, right? So if you shift the number 1 bit to the right, it is equivalent to dividing it by 2. I mean, if you divide 11 by 2, what is the number you will obtain? I mean, the decimal, natural number that we will obtain, not a floating point number. It is like 5, right? 5. You can basically cross-check these examples by yourself. It looks like shifting left has the effect of multiplying by 2. Shifting right has the effect of dividing by 2 in binary system, right? Shifting left, multiplication by 2. Shifting right, division by 2. So it has that effect. Just some shortcuts. It is the same for the decimal system, right? If you shift right 125 by 1 column, what you will have? 12. So it is equivalent to dividing that number by 10, right? So that's it. Now, let's try to, talk a bit like signed numbers. Like so far, we considered that all the numbers are positive numbers, right? We didn't talk about if they are negative or if they are positive. We just assume that they are positive numbers. So it looks like if I have an n-bit number using our formula, expansion formula. So this is like a type of, this is just 3 dots, okay? Just correction. So if I have an n-bit number, how I represent the first bit, the least significant bit. What is least significant bit? The bit that is on the most right-hand side. X0, let's say. X0 multiplied by 2 to the power of 10. X1, or bit 1, multiplied by 2 to the power of 1. We continue until we reach the most significant bit, which is xn minus 1 multiplied by 2 to the power of n minus 1. If we have n bit numbers, we can represent that number like that, right? I mean, bit 0, bit 1, and we continue until we reach bit xn minus 1. And we have, as you see, n bits, right? I just named bits like that. We have n bits. So the range of numbers, since we assume that numbers are positive, we didn't talk about their signs. What are the numbers that we can represent? We can represent numbers from 0 to 2 to the power of n minus 1. For example, if we have 3 bits, we can represent numbers from 0 to 7. Right? This is what we have seen altogether. What about sign? Like, what about negative numbers? How are we going to represent negative numbers? How can we do that? So we have two options in binary. We can have sign or sign magnitude representation and 2's complement representation, which are two different ways. But we will see the first one is not good for arithmetic. The second one works with all arithmetic operations. Okay, so let's start with sign magnitude representation. So what is the idea here? Obviously, if I have an n-bit number, as you see here, a binary number that has n bits, so I represent its individual bits as A0, A1, A2, an minus 1. I am going to use the most significant bit, or the bit that stays on the most left-hand side, as a sign bit. So if this bit is 0, the rest of the number, the rest of the bits will identify the magnitude. Somehow my computer is slow. I cannot write properly. Maybe in the break I need to restart it. A minus 1 is the sign bit, and the rest of the bits will represent the magnitude or the value of the number. So I can write things like that, basically the same formula, but I am not going to include most bit, the most significant bit, minus 1 to the power of that bit. So it's like if that bit is 0, minus 1 to the power of 0, what does it mean? What is that? Minus 1 to the power of 0? 1, right? So if that bit is 0, it means that the number is positive because that bit will not have any effect, and the rest of the bits will be counted to calculate the magnitude, the value of the number. If that bit is 1, it means that minus 1 to the power of 1, which means that I have a minus 1 here. So the rest of the numbers will be counted as magnitude, and that magnitude will be multiplied by minus 1. So that bit has an effect of making the number either positive or either negative. So it looks like if it is 1, the number is negative. If it is 0, the number is positive. Then, so let's just check an example. For example, like I have 4-bit numbers in my system. I represent numbers using 4 bits, and I am using sign magnitude representation. I would like to represent 6, minus 6, and positive 6. So how I can write positive 6? Again, like as you see, now I have 0, 1, 1, 0. So the leftmost bit, this bit is 0. It means that the number is positive. And then I put 1, 1, which is the magnitude value of the number, like 1, 1, 0 is the 6. And I have a 1, 0 here. Using 4 bits, I represent what? Positive 6. If I have 1, like 1, 1, 0 is definitely 6, right, in binary, and I put 1 here, what you see? Then it becomes minus 6. Okay, so that's so simple. Just 1 bit to represent the sign, and the other bits to represent the magnitude, the value of the number. So my question to you is, like, if I have an n-bit number, let's say 3-bit, or as in this example, 4-bit number, what are the numbers, the range of numbers that I can represent using this representation, sign magnitude representation? What is the largest positive number I can put here? Largest positive number. So I will put 0 here, right? 0. And I will fill all the other bits with 1. And what does it correspond to? 7, right? Or I can write positive 7. What is the smallest number? Yes? Minus 7. Let's again do the same, like 1, 1, 1, 1. What is that? Minus 7, right? So how how I can generalize this? How can I write the range of numbers? I can represent using n-bit magnitude representation, n-bit sign magnitude representation. We can write like that. The largest number, positive number, minus n to the power of n minus 1 is the positive number, and minus 2 to the power of n minus 1, right? Like plus to the power of n minus 1 to, sorry, like minus 2 to the power of n minus 1 to the power of n minus 1. These are the range of numbers that I can represent. It looks like I am just using or wasting 1 bit for the sign, and the rest is just used for the value, for the magnitude. Okay, any questions?
Yeah.
Yes.
Number that's on minus 1 on the lower line.
Yes. Sorry, I forgot something. Right. I mean,
Zero, right?
it is like I made a mistake. Minus n to the power of n minus 1 minus 1 was. Like we should have minus 1 here, because
My other question was
yes,
there are the difference for zeros, like if we have
exactly. We will mention it in the next slides, right?
Okay.
So as you see, if we have 4 bits, this shows you like to the power of 3 minus 1, which is 7, minus 7 plus 7 are the numbers that we can represent. Okay, so let's perform addition using this representation. Like let's add 6, minus 6 and plus 6, positive 6. If we add up these two numbers, what we should obtain? Basically 0, right? You should have 0 as a result. But let's add them using binary addition. What is plus 6? This is plus 6. What is minus 6? This is minus 6, because as you see, I have a sign bit, which is 1 here, which represents that the number is negative. Let's perform the addition. 0, 0, I have 0 here. 1, 1, I have a carry. The sum is 0. I had a carry. 1, 1, 1, 3. I have 1 here, and I have a carry. 1, I had a carry. 1, 0, I have 1 carry, and like that 1 comes here. This is the result of the addition. 1, 0, 1, 1, 1, 0, 1, 0, 0. What is the result here? So the result is also a bit ambiguous, right? I mean, if I have a 4-bit representation, it looks like there is a kind of overflow, like a number. I mean, I need to just consider maybe these 4 bits. So this bit is coming, like maybe we need to throw it away, right? If you just omit that bit, what is the result? 0, 1, 0, 0. What is that number? It is like, what? What is that? 4, right? I mean, it looks like 4 if we consider this as a result. If we consider everything as a result, again, I mean, is it like a negative number if we consider those 4 bits? It is incorrect. I mean, we don't know how to interpret the result also, right? It looks like things are not making sense at all. This is one problem. It doesn't work. We added 2 numbers, minus 6 and positive 6. The result we obtain is not 0. And it's even ambiguous. We don't know what the result is actually. And also, let's say I have 0, right? I want to represent 0. What representation I should use? Like this is also 0, and the other is also 0, right? Looks like 0, 0, 0. Sign bit is 0, positive 0, 0, 0, 0. Magnitude is 0, and I have a sign bit. It looks like I have positive and negative 0, two representations for 0. It is also an ambiguity. It is not something that we would like to have. So, you know, intuitively, this representation does not work very well, especially if we consider arithmetic operation. So we need to have something that makes more sense, that works with arithmetic, that doesn't create these ambiguities. Okay, so what is the solution? Basically, you all know it, most likely. Two's complement representation. So we are going to represent numbers using two's complement form. And using this representation, addition will work without any problems. And also, we will have a single representation for 0. Okay, we will not have any problems. So first, let's try to see how we represent numbers in two's complement form. So let's say I have a number and I am using two's complement representation. And in this case, I mean, everything that I showed for the sign magnitude representation stays the same. But the last bit, I mean, the most significant bit, the bit on the left-hand side, left-hand side, let's say, it will have actually a value. I mean, if this bit is 0, this component will cancel out and it will obviously not have any impact. But if this bit is 1, then I will add minus 2 to the power of n minus 1 to the number. So that bit does not imply the sign 0. If it is 0, it is positive. If it is 1, it's negative. Like just it doesn't have just like sign intuition. It also adds a value to the number. So again, like if that bit is 1, we understand that the number is negative. If that bit is 0, we will understand that the number is positive, but that bit has a kind of impact on the magnitude of the number. So basically, we are going to add minus 2 to the power of n minus 1 to the number, a negative number, right? So let's see, for example, if I have this value 0, 1, 1, 1, 1, 1, 1, it's a 4-bit positive number. The leftmost bit is 0, positive number. And obviously, number corresponds to what? What is that? What is this number? What? 7, right? 7. Positive 7, right? And if we look at this number, 1, 0, 0, 0, this is a negative number. Yes, because that bit is 1. What is the value of the number? What is that? What is the value of this number? How many bits I have? 4 bits, right? If you look at this formula, the bit is 1, that bit is 1, that this bit is 1. 1 multiplied by 2 to the power of what? Minus 2 to the power of what? I have 4 bits, 3, plus all the other bits, their impact on the magnitude will be as usual, right? This summation, but since I have all the bits 0, they will not have any impact. This side will not bring anything for this number. So basically I have what? What is the value of this number? What's the value of this number? Minus 8, right? Minus 8. So just look, like if I have 3 bits, if I have, let's say, 4 bits as in this example, if I have 4 bits as in this example, this bit, if it is 1, adds minus 8 to the number. If it is 0, it doesn't add anything else. And all the rest of the bits are the like bits that adds up to the positive magnitude for the number, right? So it looks like if that bit is 0, 0. If it is 1, minus 8. And all the numbers, let's say let's say the largest number I can represent here, if it is 1, 1, 1, maximum magnitude I will obtain is 7 from here. As you see, like the most, I mean, if we have 4 bits, the largest positive number I can represent here is what? 7. The smallest number, or the smallest negative number I can represent using this representation is what? -8, right? Like I put a 0 here. I put a 0, 0, 1, 1, 1. This is the largest positive number. And 1, 0, 0, 0 is the smallest number, the negative number, smallest negative number, or largest negative number, I would say. Right? Is this like -8? So that's why this is range of numbers that I can represent in n-bit 2's complement form, right? As I said, if I have n bits, like this bit will have the impact of adding -2 to the power of n minus 1. So if I fill all the other bits with 0, this will be the negative number, the largest negative number I can represent. And if I just put a 0 to this bit and I fill all the rest of the bits, basically this is the largest positive number I will obtain in this representation. Yes.
So make sure I understood. So to represent -7, the last bit will be 4.
-7.
Yes. Sorry.
How you should represent -7? Tell me.
1, 0, 0, 1.
1, 0, 0, 1, right?
Yeah.
Yes.
Okay.
And this is like -8. And this is like +1. You have -7. -7, right? So again, if that bit is 0, the left most bit is 0, number is positive. If it is 1, number is negative, actually. But on the other hand, you will see like this representation basically works well with addition. All the operations will output correct results, again, in 2's complement form. So let's say so this is what it is. Like this is an n-bit number, n-bit 2's complement number, as I show you again here. This is like the sign bit, and this is like all the bits that contribute to the positive magnitude, right? How I'm going to represent 0? What is 0 in 2's complement form? What is 0 in 2's complement form? For example, if I have 4 bits again, 4 bits, what is 0 in 4-bit 2's complement form? 0, 0, 0, and 0. There is only one 0, one representation for 0. If I have n-bit number, let's say if I have 16 bits, 16-bit number, I will fill all 16 bits with 0, and I will have 0 representation. And what is number -1? How I am going to represent -1? For example, using 4 bits, 1, 2, 3, 4, -1. I should have a negative number now. I should have 1 here, right? -8. And then I fill all these with 1s. Now what I have? -1. If I have 8-bit number, again, 1, 1, 1, 1, 1, 1, 1, and 1. This number is also -1. So basically, if you fill all the bits with 1, you always obtain -1, right? This is like the representation for -1. Again, the most negative and the most positive numbers are represented also in this slide. Again, if I have 4 bits, the most positive number is 0, 1, 1, 1, as I have shown in the previous slide. And the most negative number is 1, 0, 0, 0, because I am filling these bits with 0 so that I don't have any contribution from the digits that will add up to the positive part of the number. If I fill them with 0, I don't have any positive thing. And I put 1, I have the most negative number that I obtain. Is it clear? So if this is clear, let's try to see how we take 2's complement, or what is the impact of taking 2's complement of a number? So let's say if I have 3 in decimal, and let's represent 3 using 4 digits in 2's complement form, like 0, 0, 1, 1, right? This is, sorry, 1. 0, 0, 1, 1. This is positive 3, right? In 2's complement representation. Plus 3. Positive 3. What is taking 2's complement? I mean, what are the steps that we can have? Obviously, we can take one's complement of this number. What does it mean? We flip the bits. Zeros become 1. Ones become 0. Now I have 1, 1, 0, 0, right? And then I add 1 to this number. Like this is one's complement. This is one's complement. One's complement. I cannot write. It doesn't write well, unfortunately, today. 1, 1, 0, 0. And I add up this 1. And now I obtain 1, 1, 0, and 0. What is this number? 1, 1, 0, 0. Again, this is another number in 2's complement. So I have 3, 0, 0, 1, 1 in 2's complement form, a positive number with positive magnitude. I took 2's complement of this number and I obtain first 1's complement and then I add 1, which I obtain 2's complement of number. 1, 1, 0, 0. What is that? 1, 1, 0, 1. Sorry. You are right. I made a mistake. Tell me, what is this number? Minus 3, right? Minus 3. So it looks like if I take a number in 2's complement form, if I take 2's complement of that number, I obtain, I flip the sign of the number, right? So if I obtain, for example, if I take 2's complement of minus 3, you can do the opposite conversion. Like now, 1, 1, 0, 1 is minus 3. Let's take 2's complement of it. Like now I flip the ones, 0, 0, 1, 0. And then I add a 1, 0, 0, 1, 1. And now I obtained positive 3. This is negative 3. In short, if you take a 2's complement of a number, which is already in 2's complement form, you flip this sign. Okay? How would we take 2's complement? As we take the complement, we flip the bits, and then we add 1. This is like the method of taking 2's complement. So why this works? Why this works? So this is the explanation. So if I have a number, and if I take the complement or one's complement of the number, what I obtain a number which is full of ones, right? Like this is my 3, 0, 0, 1, 1, 1 is 3. One's complement of 3, 1, 1, 0, 0. If you add them together, you obtain a number like 1, 1, 1, 1, 1. And what is that? It's minus 1, right? 1, 1, 1, 1, 1. It's minus 1. And let's just bring minus 1 to this part and like push x to the other side. So it looks like you have this equality. So it looks like 1's complement of the number plus 1 makes negative version of the number in 2's complement form. So this is like the mathematical proof of what I was trying to say. But again, long story short, taking 2's complement of a number is like just equivalent to flipping the sign of the number. Okay? So take the 2's complement of this number, like 0, 1, 1, 0. What is like that number is 6, right? How we can take 2's complement? First, we can take 1's complement of it. Like we can flip the bits. 1, 0, 0, 1 is 1's complement of 6. Then we add 1 and we have 1, 1. We have 0, 1, 0, 1. Did I do things correctly? Yes, right? So what is this number? This is also 2's complement form. It's a negative number. Like, tell me what is this number? -6, right? -6. I mean, also, this is what I expect. It is -6. What is this decimal value of the 2's complement of this number? Again, what is this number? 1001. What is this number? -7. Not right. Unfortunately, something is wrong. -7. Let's take 2's complement of it. 0, 1, 1, 0 is 1's complement, and we add 1, and we obtain 0, 1, 1, 1. What is that number? +7, right? +7. Is it clear? So I started by showing you how to represent sign numbers, positive, negative numbers. We have seen that sign magnitude representation is fine, but it doesn't work with the arithmetic. 2's complement works with the arithmetic operations. I didn't show it yet. Let's take an example. This is the solution of the previous slide, right? Let's just check this example. So let's add 2 numbers in 2's complement form. Obviously, this is, what is that, the number? 6. What is this number? -6, right? This is -6. So basically, if I add 2 numbers, hopefully the result should be 0, right? We should obtain something 0. So let's add them. 0 plus 0, 0. 1 plus 1, 0, I have 1 carry here. 1 plus 1, 0, I have a carry here. 1 plus 1, 0, and I have a kind of number or a carry which is propagated, but I will discard it. And I have just these 4-bit numbers. Let's say we are performing 4-bit addition, and the result is 0, 0, 0, and 0. The additions work, right? We didn't have any problems. In the previous case, it didn't work. With this 2's complement form, it works perfectly. And let's use another example. What is this number? 1110. What is that? Tell me, I don't hear. Minus. I don't hear you. What is this number? As I said, now everything is in 2's complement form. What is this number? -2, right? Why it is -2? The leftmost side, let's say most significant bit is 1. Obviously, if it is 1, it's negative number. And like, if you perform the conversion, use the formula that I have shown you, it is -2, right? -2. What is this number? 3, right? So basically, the result should be 1. The addition should produce 1. Let's perform the addition. 0, 1, we have 1. 1, 1, 0, we have a carry, right? Propagated here. 1, 1, we have 0, we have a carry here. 1, 1, 0, and we have a carry here, which we will just omit. And the result is like 0, 0, 0, 1. I mean, the result fits in 4 bits, basically. Fine. Everything is fine. And this is the result of the things that I have shown. So maybe at this point we can have a short break. Let's give a short break, guys. A 5-minute break. Okay, let's see each other at 9:30. So please feel free to interrupt me whenever possible. Like, I assume that if there is silence, everything is fine, as I mentioned at the beginning of the class. All these topics build the fundamentals to understand the rest of the topics, so you shouldn't have any problems with converting numbers from one base to another, or like issues for binary arithmetic, binary computation should be resolved at this point. This is the right time to remove all confusions, I would say. Okay, so let's go back. We have seen this two's complement representation, and I would like to say, like, okay, we say we have 4-bit numbers, but what happens if we want to extend, or let's say fit a number into larger number of bits? For example, what if like I want to have a kind of 8-bit number? What if I have 16-bit numbers? What if I have 32-bit numbers in my system? Like, how I extend a 4-bit number and make it, for example, 16-bit or 32 bits. So I have sign extension and zero extension. Like, I can increase the bit width of the number. For example, if I have 3, as you see here, like 0011, a 4-bit number, basically this is a positive number, right? Positive 4-bit number. How can I make it 8 bits? How can I extend it? Since it's a positive number, so I can use, again, sign extension. I mean, if I have, for example, 8 bits, 1, 2, 3, 4, 5, 6, 7, and 8. So what was the number? Like 0, 0, 1, and 1. What will I do with the rest of the bits? Like, I had 4-bit number, but now I have 4 additional bits, right? What should I do? I should extend. What I should extend? I can extend the sign bit of the number. Since this is a positive number, so I can fill the rest of the bits with zeros, and basically I will have the same number. If you convert this number also into base 10, you will obtain 3, positive 3, no change. If I have a negative number, as you see here, 1, 0, 1, 1, it is negative because the leftmost bit, the most significant bit, is 1. So negative number for sure. How can I make an 8-bit number out of this 4-bit number? What I should do, I should extend the sign bit. That's why this is called sign extension. So I will bit the new places with its sign, with ones. And as you see, this number also, when you convert it back to the decimal base 10, you will have -5. So no change. So the rule of thumb is, when you extend numbers, when you have a kind of 4-bit number and you want to obtain an 8-bit number or 16-bit number, you should extend the sign bit. You should fill in the new positions with the sign, with the value of the sign bit. And there will be no change. The number will be the same. Magnitude will be the same, and the sign will be the same, okay? And basically, I mean, I am just saying that sign extension is the de facto extension that we will be using. But on the other hand, there will be also zero extension. In any case, you fill the new digits with zeros. Obviously, in this case, the value of the number changes if the number is negative, right? So we will do sign extension, but as we move on, we will see that when we design hardware, there will be sign extension blocks and there will be zero extension blocks. So zero extension blocks just fill in the new bits with zeros regardless of the sign of the number. But for now, we might at least omit this part, and we will just focus on the sign extension, as I said, to create, let's say, numbers longer numbers, we will use definitely sign extension so that the value of the number will not change. Okay, full stop. Okay. So just a second. Now let's consider like when we perform addition, as I mentioned, there might be overflow. So when overflow happens, how to detect overflow when we are doing arithmetics in 2's complement form. So what can be the sign of overflow? What can be the sign of overflow? How can we detect overflow if an overflow occurs or not? What can be a sign of overflow? It is written in the slides, but you know. So for example, I am adding this again. When I add numbers in 2's complement form, these numbers are already signed numbers. And as I shown you, 2's complement addition works perfectly. But obviously, there are cases where there is overflow. I mean, the result might not fit in the available number of bits that we have. So in this example, let's say I have 7 and I have 6. We add 2 numbers. So this is like 7. This is 6. And things work somehow, right? I mean, how I'm going to understand if there is an overflow or not. A question to you. So let's say I have 4 bits. I have 4 bits. 2 4-bit numbers. And I add them somehow. And let's say this is the 4-bit number I obtain. So I'm going to ask you when overflow occurs. Like if I add a positive number and a negative number, is there a possibility for an overflow? If I add a positive number and a negative number, is there a possibility for overflow? No, right? Because if I have 2 numbers, one positive, one negative, if I add them up, the result will be smaller, right? I mean, if these 2 numbers already fit in 4 bits, the result will be for sure fit in the available number. When an overflow occurs, it looks like if I add 2 numbers that have the same sign, right? So I can check, for example, this is the sign bit of the first number. If this is the sign bit of the second number, and this is the sign bit of the result. How can I understand if there is an overflow? If the sign changes, I mean, if I look at the sign bit, for example, this is 1, this is 1, 2 negative numbers, and if I look at the sum and the sign bit is 0, there is a problem. Obviously, there is an overflow because sign bit changes, it shouldn't change. If this is 0, this is 0, and this is 1, 2 positive numbers, and I add them, and the result is negative, it looks like there is problem because there is an overflow. It looks like the result does not fit in the available number of bits that we have. So that's the trick to understand if there is an overflow or not. If you add 2 positive numbers and if the sign is 1, there is overflow. If you add 2 negative numbers, but the sign is 0, there is an overflow. Otherwise, there is no overflow. Everything works perfectly. So this is a trick. So it is also the same for, let's say, for the subtraction. I mean, again, another thing that I would like to highlight, what is subtraction? I mean, how can we represent subtraction? Maybe this is something that I forgot to say in the previous slides. Let's go back if there is a slide. No, maybe this is the right point to mention it. What is subtraction? I'm pressing, but it responds me a couple of seconds later, so that's why. What is subtraction? I mean, how can I represent subtraction? Subtraction can be represented using addition, right? For example, what is 7 minus 6? It is like 7 plus minus 6, right? Actually, using 2's complement representation, I can also do subtraction by performing addition. Everything can be done as an addition operation, right? For example, as you see here, I have 7, I have minus 6. Is there a possibility for an overflow? No, right? Basically, there is no overflow. But again, like if I have subtract a negative number from a positive, sorry, a negative number from a negative number, then there will be a possibility for an overflow. Again, the same logic. Like if the sign bit changes, there is a kind of possibility for an overflow. So these are some examples for you. Like check, like we have 7-bit numbers encoded in 2's complement form. Just as a kind of homework for you, as an exercise for you, check if there is an overflow or not when you perform the following arithmetic operations in 2's complement form. You can do it after the lecture, just as a kind of cross-check if you understood everything or not. And if you have any problems, basically try to reach out to us, and you know, we can help you with the problems. So this is like the last slide of number system comparison. Again, how we started, we assumed that we had unsigned numbers, let's say n-bit unsigned numbers. Let's say we have 4 bits. If we have 4 bits, if they are unsigned, it means that we don't have any sign bit. We started with this case. What are the range? What are the numbers, smallest and the largest number that we can represent using totally unsigned representation? We started with this example, right? From what to what? From zero to 111, which is 15. So with 4 bits, you in unsigned representation, all bits contribute to the magnitude. These are like the numbers, the range of numbers that we can represent from 0 to 15, right? If we have signed magnitude representation, which means that the left bit is the sign bit, negative, positive, and the rest of the bits are the bits that contribute to the magnitude of the number. So what is the smallest? Minus 7 to 7. These are the range of numbers that we can represent using signed magnitude representation. And 2's complement, in 2's complement form. What is the largest number that I can represent? Largest positive number. What? 7. Again, from 7 to minus 8, right? Minus 8? Yes. So this is like how you can think like range of numbers that you can represent using different representations, but our concern or main, you know, representation for binary numbers, signed binary numbers, is 2's complement representation. So this is like the conclusion of at least this slide set, and we can start with the next slide set. If you have your books, please try to read these sections, 2.4, 3.2, and 3.3. And there are some sections that are talking about hardware part. You don't need to bother yourself. Just focus on this number system related explanation. Okay, so I stopped my slides on this number system and conversion. Let me try to start with like a continuation of this topic, which is, let me just stop share and start share again, just in case. So this is like the story so far that I have shown you, right? We considered numbers in 2's complement form, and this is like how we obtain the value of the number in decimal. It looks like we have the sign bit that contributes to either 0 or minus 2 to the power of n minus 1, and the other bits contribute to the positive part of the magnitude. And, you know, this is like how we represent integers, like numbers that are not fractional numbers, right? So the question here, let's just, you know, continue these slides, basically. Again, a continuation of the previous slides. I had kind of example for you. Is there an overflow if you add up these two numbers in 2's complement form? Yes or no? These 8-bit numbers. 8-bit, or how many bits do we have? 1, 2, 3, 4, 5, 6, 7-bit numbers. I would like to ask you, with using 7 bits, what is the range? Can you tell me, like, the largest number, positive number that I can have using 7 bits? It is a big number maybe, but we can write like that. To the power of what? To the power of positive number, the largest positive number, to the power of, I have 7 bits. Okay. To the power of 6 minus 1. This is the largest positive number. And the negative number, minus to the power of 6, right? These are like the largest and the largest positive number and the most negative number. Okay, so if we add up these two numbers, let's add up these two numbers. When you perform the addition, it looks like we have two positive numbers. What is the result? Is the result positive or negative? Is there a change in the sign bit? Sorry? Positive, right? If you add these two numbers, you will have a number, and the sign bit does not change. I mean, the 7-bit number you obtain after you perform addition, it looks like you will have also a positive number, which means that the sign bit didn't flip and there is no overflow. And what about these two numbers? We have two negative numbers. If you add these two negative numbers, is there a flip in the sign bit as a result? Is there any overflow when you add up these two negative numbers? Is there an overflow? So based on your answers, I am not solving the problem. You said there is no overflow here. And here there is an overflow. Just cross check. I mean, I don't know the result, basically, if your answers are correct or not. Yes.
Second example, we have the sign bit does not change.
Then it is not an overflow. The issue here is, does sign bit change or not? Okay, just check. If there is a carry, just forget that carry. Consider the number, 7-bit number you obtain, and just cross check if this is the result or not. Okay. All right. Now another story. We had integer numbers that we use 2's complement representation. What about real numbers or numbers that have fractions, like for example here, 6.75839483. We have an integer part and we have a fractional part, right? Number is not an integer only. it has also a fractional part. So we will see also, this is just a side note. Sometimes, for example, we have a famous number, right? Pi. And that number is also a number that has like infinite number of digits after fraction. It is like a number that's, right? You continuously put a digit. You have infinite number of digits for this number. How can we represent such numbers, for example, with our limited number of bits? It looks like also we will have an approximate representation of these numbers. How? I will show you, but let's just move on. Let's try to see like how can we encode real numbers? How can we do that? We have two common notations like fixed point and floating point representations. What does it mean? What does fixed point mean? What does floating point mean? Let's try to see. So let's see fixed point representation. What is that? So it's pretty straightforward. Like if I have a k number of bits to represent a number, for example, 4 bits, 8 bits, 16 bits, it looks like f bits will be used to represent the fractional part, and the remaining k minus f bits will be used to represent the real part, the integer part of the number. It looks like this point that separates fractional part from the integer part is fixed. So I have exactly f number of bits for the fractional part and k minus f number of bits for the integer part. That's why I say fixed point numbers. The point is fixed. Okay, so that's the idea. So what does it mean? Let's say I have 6 bits, for example, and I am going to use a fixed point representation in which 3 bits will be used for the integer parts, like I will use 3 bits for the integer part of fractional numbers or real numbers, and I will use 3 bits for the fractional part. And as you see, the point is fixed. That's why I say fixed point, okay? So let's say I have this number in fixed point representation. Again, like 101.100. This is like a fixed point number in binary, base 2. How I can obtain the real number in base 10? Basically, the real part, I mean 3 bits that contribute to the real part, the conversion is the same. Again, 1 multiplied by 2 to the power of 0, 0 multiplied by 2 to the power of 1, 1 multiplied by 2 to the power of 2. So this is, as you see, the integer part of the number. And now, what about the fractional part? Now, this one will be multiplied by 2 to the power of minus 1. This 0, like 0 multiplied by 2 to the power of minus 2. This 0, 0 multiplied by 2 to the power of minus 3. As you see, like obviously, since these bits are 0, they have no impact. So this part, 101, what does it correspond to? 101. What is that? 5, right? 5. And I cannot write. Anyways, 5. And this like 0.100 corresponds to 1 multiplied by 2 to the power of minus 1, which is like 0.5, right? 2 to the power of minus 1 corresponds to 0.5, or 1.1 over 2. So this is like 0.5 plus 0.5, you obtain 5.5. So this is how we represent fixed point numbers, okay? For example, another thing, like now I have a kind of, again, fractional number, real number in base 10, how I convert it to binary, how I can represent things, again, using 3 bits. 3 bits are dedicated to integer part, and 3 bits are dedicated to the real part of the number. We have fixed point representation, 3 bits for the integer part, 3 bits for the real part, okay? How I am going to do that? Again, simple. This 6, let's first convert 6, the integer part, into binary. 6 is like 1, 0, 1, 1, 0 in binary, right? 1, 1, 0 in binary. And how I'm going to represent 0.125 in binary. This is like base 10, right? So in this case, how I was calculating, converting the number in base 10 into binary, I was continuously dividing, right? We had the division-based algorithm, but since this is fractional number, now we are going to multiply it. So 0.25, I multiply by 2, I obtain 0.25, and I just record integer part. Now I have 0.25, I multiply it by 2, I have 0.5, and the integer part is 0. I have this 0 here. And 0.5 multiplied by 2, I obtain 1. I removed all fractional part, as you see, and the integer part is 1. So basically what I put in this order 0, 0, 1 to here. And I have basically the fixed point representation of this number. Clear? Is it clear? Any problems? So this is like the algorithm that you can use for conversion. Now, let's do the same for 6.75. And let's say now we are using 4 integer bits and 4 fraction bits. So we have 4 bits for integer and we have 4 bits for the fractional part. Okay, so my question is like integer part, 6. How are we going to represent this in binary? What is that? We already did it, right? What is that? 0, 1, 1, 0, right? I'm not making a mistake, I hope. 0, 1, 1, 0 is the integer part of the number in base 2. And what about fractional part? So what I'm going to do right now, I'm going to multiply continuously, right? 0. My pen is not writing very well. Maybe I can show you that just the result. Maybe it is better to solve together. Let's do it like that. 0.75 multiplied by 2, what I obtain? 1.5, right? And now the integer part of this number is what? 1. I record it. And now what is the fractional part of this number? 0.5. Right? 0.5. Now I multiply it by 2. And what I obtain? 1. So this is also the digit that I am going to put. So I can put like 1 and 1. And the other digits will be 0 because I don't have any contribution from the other digits. And this is my conversion, 0.1100 in base 10. Base 2, sorry, binary. This is how you can see things. Also, you know, if you write this number, what is that? Like this is 4 plus 2, right, plus 0.5 plus 0.25. You can also cross check, and this is like the number that we will obtain, right? If you make the conversion. Is it clear? Basically, we are using the same stuff, but we are now considering the fractional part of the number for conversion. And we are doing conversion separately. First integer part, then the fractional part. Yes?
Because we are considering plus or minus.
Not yet. Not yet. And now this is your, let's say, concern, right? Now how I'm going to represent negative numbers. How can we do that? How can we do that? Like before, right? I mean, we can still have, for example, sign magnitude representation. In this case, what can we do? We can, for example, dedicate again the leftmost bit, the most significant bit, as the sign bit, right? We can do it basically. I mean, if we have a 4-bit number, like again, 4 bits for the fractional part and 4-bit for the integer part, maybe the leftmost bit of the integer part can be used as the sign bit. Or maybe we can use 2's complement notation. So again, which one to use, basically, how to use them. So still a bit ambiguous, right? If we have fixed point numbers. For example, let's say, let's first convert like 7.5. Let's try to convert it into fixed point number, right? What is that? What is 7? 0, 1, 1, and 1. Point, what is 0. What is 0.5? I can put a 1 here, right? 0, 0, and 0. I mean, this is, sorry for my handwriting. So this is like positive 7.5, basically in fixed point representation. If we use sign magnitude representation, maybe, you know, this bit can be considered as positive, negative bit. So maybe, you know, I can represent like 1, 1, 1, 1, point, 1, 0, 0, and 0. So this is negative 7.5 in sign magnitude representation, not 2's complement representation. So as you see, this is the sign bit. Or let's do 2's complement. Let's see if it works for 2's complement. Like it should work. I mean, this is like my overall number, right? All the bits in fixed point, 4 bit for 4 bits for fixed real part, 4 bits for integer part. I just invert, takes 1's complement, and I add 1, and I have this representation again. This is like, this can be the same number, the same fixed point number in 2's complement form. And this can be minus 7.5. Is it clear? So the question is like, is addition and other type of operations work well in this type of representation? A question to you here. We can check it later, maybe together. But using fixed point number, we have like these two options as we had in normal standard integer numbers, right? Sign magnitude representation and 2's complement representation. So I would like to ask you, before jumping to floating point representation, what is the limitation of these fixed point numbers, the number representation? What is the limitation? As I said, for example, if I have 8 bits in total, I devote 4 bits for the integer part and, for example, 4 bits for the real part. Of course, the location of this point of this dot can change. I mean, I can say, okay, I will dedicate 3 points, 3 digits for integer, 5 digits for the real part, vice versa. But what is the problem that you see here in this representation? Is there any problem? Exactly. This is a problem, right? I mean, you see, I don't have so much space. The range of numbers that I can represent using fixed point representation is not that much. It's, I mean, if I have a very large number, I mean, large number means like if I have a number, for example, 0.1, 2, 3, like a pi, right? Number pi. How can you represent? You don't have a kind of a strong representation using this fixed point representation, right? It is like something that limits you. How can we represent very, very, very small numbers or very, very, very large numbers? We need definitely a more systematic representation. So that's why we have floating point representation, like representation for non-integer numbers, as I mentioned, including very small and very large numbers, floating point representation. So let me just show you one slide, and then I will conclude today's lecture and we can continue on Wednesday. So just let's say high level of the idea, general idea. Let's say if I have a very small number, for example, 0.02.34 multiplied by 10 to the power of minus 6, 10 to the power of 56. This is a normalized representation of a kind of real number. What is normalized representation? As you see, we have one digit and a point, and the rest of the number multiplied by a kind of power of 10. So this is scientific representation. So it looks like if we convert numbers in this form, we can encode them in a more efficient way using the representation that I'm going to present. So for example, this is not normalized number, but we can also put it into normalized form. Well, how can I write? Even though it is a kind of not a real number, like this is not a real number, right? This is an integer basically, but I can represent it like that, right? 9.8702 multiplied by 10 to the power of what? 10 to the power of 11, right? So I can put all the numbers in this form, in this like normalized form. This type of representation, then I will show you how to encode it. Basically, we can do the same for base 2. Again, I can represent the number like 1 point something in base 2 multiplied by a power of 2. A power of 2, as you see in this example. If we convert, or if we change the notation, if we represent our number using this scientific notation, then we can encode it very efficiently. And it also enables us to represent very large or very small numbers using fixed number of bits. We will see it. So what is the encoding mechanism? What is like the way we represent floating point numbers? We have a standard from IEEE. It is defined, it is represented in 1985. It is a kind of, indeed, an old standard. Basically, if, for example, in your programming language, in C, if you define float or double variables, right? These are numbers or variables that represent floating point numbers. Basically, everything that you define, float or double, will be represented using this encoding, this notation, okay? So it looks like using this standard, we have a standardized way to represent these real numbers across programming languages, computing systems, I would say. And we have two type of encoding representation. Single precision, it looks like everything will be encoded into 32 bits, or double precision, which will will encode everything, all, let's say, the information into 64 bits. Obviously, they will offer you different ranges of numbers, like very large and very small numbers, represented in floating point representation. So this is like the slide that I would like to stop today, and we will continue on Wednesday. Okay. So far, that's like the point. After this topic, we will have an additional lecture on digital logic, and then we will jump into instruction set architectures and start exploring RISC-V architecture. Okay. See you on Wednesday.